Mhm.
So if we take, can
I
you
have an intuition.
identity matrix, would that work? The column vectors are orthogonal, uh, plus the norm of a vector. Yeah,
Go ahead, Atharva. What's the intuition you have?
Yeah. So our original basis vectors were 3 unit vectors perpendicular to each other, right?
right.
So if any matrix, let's say
You
3
guys
cross 3
continue. I'll be
matrix,
back in a
it
minute.
shows,
Atharva,
Yeah.
Atharva and
yeah,
Chetan can route the discussion. And after that, you continue with the linear algebra questions.
Understood, sir.
Go ahead.
yeah. So let's say a 3 cross 3 matrix. Each column shows where I cap is going, where J cap is going, where K cap is going. So if my if the first column, second column, and third column are 3 unit vectors which are perpendicular to each other,
Right.
that means I am taking my basis vectors which are perpendicular to each other and just kind of rotating them,
Correct. Correct.
just
That
flipping them.
that's
Yeah.
what I said is so.
So that should kind of preserve the
We can try
dimension
it
of
out. We
the.
can try it out, and we can see if it is correct or not. Let me
Yeah.
open GeoGebra. So that's what my intuition was for the matrix. I don't know if it's correct or not. Let's see. Let's figure it out. We'll see.
Hello.
Yes, Swapnil.
What are we doing?
Okay. Okay. So, good evening, Vinay. So the thing is, we discuss vectors and eigenvalues, right? So when eigenvectors are such vectors that when inputted to a matrix, they give the scaled version of themselves as the output, right? So that those are eigenvectors. So there are matrices which, when we input a vector to, give they preserve the norm of the vector. That's the magnitude of the vector. We had to come up with such a matrix. And the another thing about such matrices are that their columns are orthogonal to each other. So me and Atharva think that identity matrix are such matrices. We are trying to see if that's true or not.
Yeah, I was just watching one of the tutorial.
Hmm.
I think they were talking about this. Like some diagonal matrix only rotates, and if you take some magnitude instead of 111, then they change the magnitude of the vector. And if we take like 111 and like 1 minus 1 and 1, and if you multiply it with some vector, then it only rotates that vector. Could you please check that? Like
No,
instead.
no. We're not saying that only the diagonal matrix changes, rotates the vector. We're saying that if we take any 3 perpendicular vectors and make any 3 perpendicular unit vectors as the columns of matrix M, then we can get maybe uh, this resultant vector of the same magnitude.
Think that they have to be unit vectors.
They just have to preserve the norm of the vector. That's it. If we have other examples as well, we'll try to figure those out as well. So if you
So we need to find a rotation
I
matrix.
think all permutations of the identity matrix would also work, right?
Permutation.
Like if you just like interchange the rows, that is, you have 6 possible. The magnitude will remain the same, right? But
So what does it mean? Okay, let's think about this for a minute, right? The first column is just telling you where the I cap is getting mapped to, and you know whatever happens to I cap happens to the entire space. So you're saying the first column should be of norm one, right? Because you want the identity matrix wherever it shifts to, it should preserve the norm, right? That's what it's trying to say. So
Right.
whatever is in that column, it should be of norm one. It can be anything, but it should be of norm 1. Does that make sense? For now, I mean, that's the first thought I get, right? Because if you're taking if you're taking any vector and trying to input to the matrix, you can think of it as taking I cap and inputting it to the matrix. Is there a lot of background noise from my end? I have my fan on. Just want to
Nothing.
know. Okay. So I cap, J cap, and K cap are already present in the matrix column itself. Like you already know where I cap is getting mapped to. So if I think of where I cap is getting mapped to, I just have to make sure that I cap gets mapped to a unit vector. Because when starting it was a unit vector. Even while getting transformed, it should be a unit vector, right?
Right.
I'm not sure
Yeah,
about
yeah. So, okay,
perpendicularity.
your answer is so the columns of the matrix should be unit vectors. So any
Yeah,
such
yeah.
matrix.
I'm not sure about perpendicularity. I just think
Wait, what's the perpendicular condition? I think maybe the question.
someone was saying that let's take 3 vectors that are perpendicular to each other. Maybe they might do the same thing, right?
One more way we can think of it is like uh, we can see what a matrix is doing to I cap, right? So if the matrix is not scaling I cap, it is not scaling J cap, and it is not scaling K cap. And all of those 3 are perpendicular as in the original case.
But
Because
I don't
if
understand
they're
the
not
perpendicularity.
perpendicular,
Yeah.
if they're
So
not
you
perpendicular,
should have a like the column should form be the basis
Okay,
such that
so you guys open
have the
GeoGebra.
same thing, right?
Let's open GeoGebra and then realize what Atharva is saying. Come out with a orthonormal vectors. Write them as columns in the matrix. Okay, and see these vectors, how they look like in R3. Okay, each one of you cook up your own orthonormal vectors, non-trivial ones. Of course, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1 that you were discussing are trivial ones.
Yeah, yeah.
Try finding something, write something non-trivial. You can always do that, right? Write some random vector for the first column, pick something that's perpendicular to that and call it in the second column, and then in the third column.
I think
Atharva,
It's
you
like
guys are good at doing this in your JE preparation. Maybe you should be able to do it fast. Help them with non-trivial looking matrices that are orthonormal columns. And let's plot them in GeoGebra. And you tell them what exactly you meant there. You have the right intuition.
yes, sir.
they should be just like the coordinate system just rotating tilted towards a different orientation.
Mhm.
That's right.
We just want the norm to be preserved. The other transformations can obviously happen. So identity matrix will obviously give us the vector itself. We don't want the trivial solution for that.
So I guess like even if you do, I mean, permutations of the identity matrix also you'll get the same thing. Like that's also correct, right?
You mean
I don't think it's wrong.
the identity matrix.
Like the rows, like you have different orderings of the row, like identity matrix with the rows having different orderings. That is, you'll have 6 such matrices, including the identity matrix.
Yeah. Right. So, but we want some other.
Yeah, he said that. Yeah, I mean, it's a trivial case. Identity matrix and like matrices similar to that are the trivial case. Maybe we'll go with what Srivini suggested. Like you fix one column to have unit norm, and then I mean, like yeah, the only thing that I get reminded when I do this question is maybe we shouldn't go there. Yeah.
Does 0.30 and 0.9 make it a unit vector?
0.30.
Oh wait, I think it only adds up to 90. So okay, so you need you need the column to be summing up to 1, right? The square of the column, I mean, square of each element in the column should add up to 1, right? Okay, then we can just do the sphere thing and take 3 points on that, right? Is that okay?
Keyword.
No,
No, but
sphere,
this
sphere.
one, but they have additional condition. Yeah, but sphere will somehow help us
Sphere
for the
will tell us every vector that is a unit vector, right? That's what I wanted to.
and but
Write all the conditions of the question. I think I'm missing it out. Like if you want, I will take the writing pad or someone can just write it down. Like I
I
think I'm
think
missing.
we can just
Oh.
take a random plane maybe and take a random point on that plane.
And normalize
We
it.
can we will get the normal and
That's
we can
that's
find
all.
both.
That's very again similar to Gram-Schmidt's orthonormalization. See,
Yeah,
these things keep
Oh yeah,
coming
right.
again and again and
I
again and
remember
again. So,
that.
yeah, you people should not work by memory. You should work by intuition. You should remove
Yeah.
Gram-Schmidt's and make it Atharva Mahajan process or Sri Vinay Sridhar
Sir,
process or
like
Maria Paul
I
process.
actually tried I tried deriving the Gram-Schmidt formula once, like on my own. Like
Yeah,
it took
it's
me
easy
a lot of
doable.
time. It took me like
I-
2-3 hours, but yeah, I kind of got it.
Yeah, if you have done it before, it's very easy. I remember Atharva doing it in my cabin, right, Atharva?
Yes, sir.
Yeah, it wasn't
What?
like I imagined it to be way more complicated, but we tried it
No.
once
See, what
during
we
our
are
session too.
you know something, what we are doing here is much easier than Gram-Schmidt's. What we are doing is you simply take a vector. Okay, let's do it. All of you take a vector, give me a vector, normalize it. Okay. Second thing, solve take the vector a comma b comma c, and then solve for the equation ax plus by plus cz equals 0. Then you will get something perpendicular to it, x, y, z. It should not be zeros, all zeros, some non-trivial,
Yeah,
non-origin point. उसको normalize करो. Normalize करने के बाद pick a vector perpendicular to the plane passing through these two vectors. That's all. Pen and paper work. Nishan, maybe Nishan alone can use the board. Others can use pen and paper. And because Nishan has such a big board, I've never seen him use. So Nishan, go ahead. Go ahead, write on the board and figure it out. So give me 3 vectors and let's plot that on GeoGebra and then see how it works. Guys, I'm a little tired today. I'm lying down and talking, so I'm not keeping my video on. I hope it's okay.
Yes.
right. When Nishant's in a different room, usually you're in a different room, right? Than you're usually in.
No, I don't think so. He just switched his camera in a different place because it used
The
to be
whiteboard is
dark,
bigger.
but then I see
Yeah, the whiteboard, yeah.
The whiteboard has always been there, you know. This was the whiteboard was the only plane on which my shadow would be there.
Yeah.
So I've just changed some setup of my room.
Oh, right, yeah.
I think you changed the light first. That's the best change that we could see.
Lights are in the same place fixed. I've just changed the location of my computer. That's all.
But it used to be very dark previously.
That's why I changed the location. I used to, the light would directly come to my eye and I used to feel tired out of that. That's why I changed so that light is just behind me now.
Are you
Okay.
available to share your screen or are you busy? I see that you're busy.
No, I'm not busy.
Okay. So I
I'm
wanted you to share maybe and show us.
Sure.
Yeah.
Mhm.
No, I was writing down on my pad. I saw. Anyways. I
I was just joking, Nishan. Use whatever.
One second. I'll be sharing it. Okay, let us do two vectors, make a plane out of it. Okay, 1 Vector Chetan,
Let's take 1 to 1.
1 to 1.
Then maybe we can
V2.
take 5, 12, 13. I mean, we have to normalize it too, right?
So we should take instead of 1 to 1.
5, 12, 13.
Okay.
And 3, 4, 5. It'll be
5,
easier to normalize it. Yeah.
5, 12, and 30. 30.
Yeah. 1, 3, 1, 3.
1
1,
to 1
3.
was not normalized, right?
Hmm?
1 to 1 was not normalized.
It wasn't like
Mhm.
you'll get a root quantity in the denominator, right? But here you'll get a
Not a
perfect.
perfect square.
Yeah, yeah.
Experience is speaking.
Pythagoras theorem. Pythagorean triplet. No, not triplet. 4, 5,
Yeah,
6
it's
is
triplet.
2,
Yeah,
3, 4, 5 is triplet.
3, 4,
Anyways,
5 is triplet. 5, 12, 13 is also triplet.
No, one thing, I think we wanted to take one vector and normalize it, find something perpendicular.
Oh, yeah. That. Okay, yeah. Then. Okay, yeah. Then you can't do that. Yeah. You probably can't.
Any
Yeah.
vector would
so
work. You need not worry about what vector you are choosing. We just have to normalize that, find out the vector perpendicular to that, make a plane, find out.
okay, this way. Okay,
We just need
fine.
3 orthogonal vectors. That's it.
Okay, Chetan, what was the vector?
Any random vector. You take 3, 1, 5. You take
3,
1.
4, 5.
Fine. Okay, let us normalize it.
3.
Yeah. 0.6, 0.8, 1. No. Sorry.
Okay,
When you normalize it,
So the normalized would be 0.42, 0.57, 0.71.
0.42.
0.57, 0.71.
okay, it wasn't. Yeah, I think my.
Sorry, this should not be the conclusion now. How to represent norm?
Yeah, go ahead.
But the height.
Okay, another vector.
No, now you have to, so now we want to find a vector that
Plane.
is perpendicular to this.
Yeah.
Okay,
Any
so
vector
V1.
that lies on that plane.
We can do this in a row, V1 in a row, and do X, Y, Z and equal to 0, right? That's what we were doing, right? To find a vector that is perpendicular to a given vector.
Okay. V1.
Yeah, write it as a row, write it transpose, V1 transpose. Yeah. Okay.
Is equal to
0, right?
0.
We want,
for perpendicularity, fine.
other than the trivial solution, we want to find some other X, Y, Z. Yeah. You can just do -5, 0, and 3.
Yeah, that was.
Yeah. That works. Or 0, -5, 4. No, -5, 0, 3.
So the V2 norm is
The
Nishan,
vector is
Nishan.
-5.
0,
Yeah.
5, -4 would work as well. It's just
-5, 0, 3, not 2. Like you made a typo.
Yeah.
okay.
The normalized one is 5 square 25.
And yeah, we just need one, right? Yeah.
Which is now 36, 6, 5 by 6 minus 5 by 6 is Chetan.
just a second. So it's minus 0.86, 0.
Minus 0.86.
0.51.
Okay.
Perfect.
So now we can take the same thing that we did. We can take V1 and V2 as the two rows. Yeah, no. So what we want to do is stack up the V1 and V2 on top of each other, right? Because we want what is perpendicular to the plane. We want it perpendicular to V1 and V2, right?
So
Yeah.
So write V1, below it write V2, and then write this as a row vector, two row vectors, right? So you understand? V1 transpose and V2 transpose. It's stacked up like that.
okay.
Mhm.
So V2 is -503,
Yeah,
and V1 was
3, 4, 5.
345. Fine.
Right, and now we're trying to find XYZ that is perpendicular to both. So write a column vector XYZ.
Yeah. This only, no?
Yeah. Chetan, do you want to maybe explain what we're trying to do here?
Okay,
Or, yeah.
it's okay. Yeah, I'll quickly brief what we are trying to do here. So we have eigenvectors when inputted to a matrix, they give us scaled versions of themselves, right? Just like that, we have matrices as well, which when input is given to those matrices, they preserve the norm, that is the magnitude of those vectors. So we are trying to figure out a matrix that does that. The special thing about such matrices is that their columns are orthogonal to each other. So we are trying to find out such matrix. So we took one vector, we took the norm of it, that is only the magnitude of it. We took the vector. Afterwards, we took another vector that is perpendicular to that. We just multiplied it with variables x, y, z such that they give us 0. We figured out what those x, y, z are, and we have two vectors. We are trying to do the same with them. We are trying to find out the third vector that is perpendicular to both of them. So we have written down those two vectors as the rows of the matrix, and our x, y, z, we are trying to figure out x, y, z such that they give us 0 for both. That's it. Is there anything else, Vinay?
Can we see them as rotational matrices in this dimensional space?
I don't know what rotational is.
No,
Like, I
means
don't think we've discussed that,
what I'm
right?
saying, no, not the idea, the geometrical interpretation that I'm getting is, if we do this thing like this was our what this XYZ plane thing, no? This
Mhm. Yeah,
um
the three axis, yeah.
yeah, and after what we are saying essentially is maintain their magnitude for the input vector. Yeah,
Yeah.
input and output vector should have same magnitude. So essentially, how we can uh get that thing is we don't change this thing, we just rotate it.
Rotate it. That's it.
The relative basis means the constructor remains the same, they are still orthogonal. That's why this
So the
is,
norm is preserved. Yeah, yeah, correct.
yeah. It is only feasible when there is a sort of rotation, or
So the
just
matrix
just
itself is a
geometry.
rotational matrix. Is that what you are suggesting?
Yeah, can we say it as rotation matrices only?
So it
I think
happens
you're right. Yeah, makes sense
every day,
actually.
right? So all of us use phones, Android phone, iPhones, right? You're holding a image. It's a 2x2 grid, all the pixels, RGB or grayscale, right? And it
Mhm.
has a gyroscope. The moment it recognizes that you kind of holding the phone this way, there's a matrix operation that happens inside your phone that rotates the image without really changing the dimension of it, right? I mean, assume your phone is kind of square, right? So I think, such a matrix.
Your image may not be like a square matrix, right? It can be a rectangular,
Yeah,
but
but
even Yeah, I
Correct.
guess the norm of the vector is only preserved. Maybe the dimension of the vector can change, I guess, right? Like with space, it is in.
What is this going on?
Nothing.
Okay, okay.
AI companion summary. That's it.
Oh, okay, summary. Okay.
It was weird seeing my full name.
Okay. All right. So we'll know what we are talking about.
Yeah.
Yeah. So anyway, so I think if we take a vector, multiply with a matrix, let's think of a vector in a R2 space, and we multiply that vector with a matrix containing the rotation. So that way it will rotate, but will not change the magnitude, right? So those are all special vectors, also similar to what we're discussing here. Kind of related concept, not exactly the same. Here we're talking about eigenvalues where once it is applied, it will not change the direction, only the magnitude, right? The other one is it will not change the magnitude, but change the direction, right? It's kind of
Is it? No, I don't think it's specific to a matrix like before, right? I think eigenvectors are specific to the matrix, but now we have to change the entire matrix to be able to preserve the norm, right?
Yeah.
The matrix itself,
Like
not every
what
matrix.
Ankit actually, I don't know if you were there. Like, what Ankit suggested is that if we use any rotational methods, it satisfies these properties, right?
Yeah,
So that was
In the
his
end-
idea. I think it's correct.
Yeah, in the end, you just need vectors that are preserving the norm in the matrix itself. The only thing I don't understand is about the orthogonalization. I mean, does it have to be that the three vectors in the matrix are orthogonal? I am not able to see it clearly. Maybe I need to think about it.
No,
Uh,
Shivin,
is Atharva around? Atharva, you
Yes,
gave
sir.
a very quick answer to the question. I mean, that's all it is. The intuition version of whatever we are discussing. Why don't you explain that using GeoGebra?
Okay, sir.
Just take three vectors quickly and show that on GeoGebra. And after that, you guys can discuss and see what is happening. Atharva had a very straightforward version. That is actually the version. It's a very scary term, orthonormal vectors for becoming the columns of a matrix, right? But then it's actually very trivial. The intuition that Atharva gave. So Atharva, take over for just 5 minutes, explain the idea, and show how it's norm preserving according to your intuition. And
Yes.
all of you can together try doing it the mathematical way, just for fun. I'm sorry if I barged in between your discussion. I don't know what you guys were discussing. I just thought Atharva had that quick idea. I wanted you all to know it, and I'm also taking note of it to include that in my module.
I think the idea that the norm should be preserved, the first thing that comes to mind is that I cap, J cap, and K cap's norm should be preserved. So I understood that part. But the perpendicularity part is kind of getting it's into my brain now, because if I think about trying to get R2 close, then I feel like all the vectors inside them would actually scale up. Even though these two vectors preserve their norm.
So I think we can do it in 2D first, maybe.
Okay.
That way we can like see why non-perpendicular, why we need those vectors to be perpendicular.
Kind of like squishing the space will always lead to some vectors getting larger than itself.
yeah, that thing also, and that thing also that we saw a few days back in that, if you remember the null space and particular and that solution thing also. And one more place we saw this thing.
So we are taking two vectors making a matrix out of it. Fine. And of course, we are going to find something perpendicular to it. Just general things.
Okay.
So we have taken two vectors and we are trying to find a plane perpendicular to both of them.
No. This is just two vectors, which are the column vectors of the matrix V1 and
Fine.
V2.
We won't
Fine.
find a plane perpendicular to this. We are working in R2, right?
No.
Hmm.
I think we should look at it in 2 dimensions before we move to 3 dimensions.
No.
That way it
I
would
was
be
just
clearer.
clarifying to Nishan. I wasn't
Mhm.
saying that to you.
Can we take the columns of the matrix to be in unit norm? Because I mean, I think it's clear that the matrix should have unit norm, but it's not clear whether they should be perpendicular or not. So
Yeah. Is there a way that I can make
you can
these
do that.
vectors unit vector?
Yeah. You can just draw a unit circle, right? X square plus Y square plus Z square. I mean, X square plus Y square is equal to 0.
1 by root 2 is 0.707. So that 1 can be 0.707, 0.707, or 71 if you want to.
Yeah, and you can take the vectors on this. Maybe you can actually move the vector, or actually it's better if you can make points on the circle. So make point number 1 on equation 1 and write the vector to that point. That will be better. Yeah, and take one more point. And now you can draw vectors to it. So vector of P1 and P2. No, just do vector of vector bracket P. Okay, that works. Did that work?
Yeah.
Okay.
Okay, but how can we put it in
Oh,
the matrix?
forgot that. That's not. It doesn't work as V1 comma V2, right?
Yeah.
Okay, take easy points on that circle and write it physically, right? If that's okay.
There is one way, but it will be lengthy. We'll have to take dot product with I cap and J cap.
You don't have to think too much. So you take the y-axis 0, 1. We know that's going to be on the circle, right? The other one would be 1 by root 2, comma 1 by root 2, which is the 45-degree angle, which is 1 by
No,
root.
but
Yeah.
we would like to change that also, right?
Which one?
Both of them.
Oh, okay, you want to move the point. Okay, all right.
Yeah.
So then the equation will be, kind of x square plus y square equal to 1. So you just have a different x and y. So x can vary between 0 to 1, and y will be square root of 1 minus x squared. That's all.
Yeah, I think.
आता ही नहीं है
Okay, I think we have the matrix.
Maybe you can show it so why it is not true.
Okay, so
Yeah, I mean, sorry to interrupt the flow, but I didn't actually understand why the columns itself had to be orthonormal. Like, I didn't get that.
Hello,
Column.
yeah,
Atharva,
yeah.
could you
Yes.
please tell me that what I am thinking is right or wrong? Why we need a orthonormal matrix that? If we take a vector, we can always decompose it in a three vectors, subvectors.
Yes.
So we want to preserve that ortho perpendicularity to each other. We just want
Mhm.
to change direction of it, like from its opposite direction to change.
Yes,
Like
yes.
if we are three perpendicular vector x, y, g, so we just want to like g to minus g, so that we can change it from one quadrant to another quadrant.
Hmm.
And
Yeah,
also
so
normal form. Yeah, go
if you change z to minus z, in that also the three vectors that we have, they're orthonormal only, right?
Yeah, we just we are just uh, changing uh,
To norm of you. Yeah.
Yeah. Change their colors. Okay, so we have a random vector u here, and this circle is basically a circle of modulus of that vector. Now we'll just adjust these two vectors v1 and v2,
Can you just put the angle between
and we'll
V1
see.
and V2?
Yeah, and as it comes to 90 degree, I'll do that also. Then yeah.
Well, what is the broad idea? What are we doing?
We are just trying to see that these vectors should be perpendicular and of unit modulus.
So what is the criteria for those vectors to be perpendicular?
So guys, this is a very
That's what
easy concept actually. All that we are doing here is the transformation is ij becomes some two vectors that are perpendicular. That's all is the idea.
yeah. So when this is a 90-degree, it touches the circle approximately. As
Yeah,
you
it should
increase,
touch because the norm should be 1, right? When
Yeah.
this is the transformation, any vector, such a transformation will simply move by that angle. That's all. Right? This is a no-brainer. But if you are worried about jargons, you may not understand what's happening there. Forget linear algebra also. See it as a function. If I cap goes to a vector on a circle and j cap goes to another vector on a circle, and these two vectors are perpendicular, then it means that every single vector, as per this transformation, simply gets rotated. That is not the case if the angle is not 90 degrees. The norm will change. Otherwise, the norm does not change. Right? What does it happen in 3D? What is it in 4 dimension, 5 dimension, n dimension? Just have this intuition that orthonormal matrices have this great property that they preserve norm. That's it. In your subject, computer science especially, 1 in 2 matrices they encounter are orthonormal matrices.
Maybe another way to think about it is when we multiply a matrix, essentially we are doing a linear transformation, and linear transformations basically do two things to a vector. Either it will expand or contract the vector, and then it will rotate the vector. And most of the time, the linear transformation will do both. So I guess there are special cases where either it will only rotate, or it will only kind of
Scale.
will not rotate. only
Yeah, scaling is the case when you have eigenvectors.
No,
I
I
think.
wouldn't want to think of it that way, right? Because see, there are rotations where, so, okay, I mean,
Maybe I
there are
should explain the problem first. The problem at our hand is that we are given two vectors and we are taking the norm of them, both of them, isn't it?
What we're trying to do is like the idea of eigenvectors is that when we apply the metrics to the vector, you get a scaled version of the vector. So now
Fine.
what we're trying to do is we are going to apply, we don't know what the matrix is, but when we apply that to the vector, we actually get the same, get a different vector having the same norm, and we're trying to find out what the matrix is. So as of what we've discussed now, identity matrix is an obvious case because the same vector will have the same norm as the input vector, right? So when you
Correct,
apply
correct.
the identity matrix, it's obvious. Then what you can think of is something like if the rows of the identity matrix are interchanged, then you'll get like if it's 1, 2, 3, you'll get 3, 2, 1 as your like if so no if the rows of your identity matrix are interchanged, you'll get if it's 1, 2, 3, you'll get 3, 2, 1 depending on how you interchange the rows. Right? That is, maybe if you want, you can, so those are like the trivial cases that we can think of. But the general case is that we are trying to like the answer is to the question is that when we have we know that the columns of the matrix are where I cap and j cap, like the first column tells us where I cap is mapped to, and the second column tells us where j cap is mapped to. So what we have understood, like what Atharva actually suggested, is that we take a matrix whose columns have a unit norm, and the columns themselves are orthogonal to each other. That would be your answer. So Srivinay's doubt was that why do they need to be orthogonal? But I didn't actually understand why they needed to be of unit norm either. So like I'm a bit confused about that. So that's the conclusion of the discussion we've done so far.
Very
So,
hard. It's
so
not
there is a question and there is another thing is approach. The question is that we are taking a vector multiplying to a random matrix and we are getting another vector whose norm is same as the
Unit
parent
vector,
vector.
input
Fine.
vector.
In this case,
Input vector.
I like Deversmith says explanation on this. So when we do linear combination, we are getting two things here. One is our vector is getting scaled, and the other thing is it gets rotated, right?
Fine.
It need not lie in the same line. It
Correct.
can lie somewhere else as well. So
Hmm.
when it's lying somewhere else, we're saying it got rotated.
Right.
We have two cases there. One is it only rotates it, or second is it only scales it, right?
Okay.
So the second case we have already discussed when we discussed eigenvectors. Eigenvectors are such vectors when inputted, they get scaled,
Scaled.
right?
Fine.
We are trying to look at the first case, that when it only gets rotated,
Only gets rotated.
right? The size mean the norm
Rotated by 90 degree.
right. So not 90-degree, it only gets rotated, that's it. That's our only concern. The size should be norm of it, that's it. The norm should be preserved. Yeah, go ahead with it.
Size should be norm of it.
The norm should be preserved, the size should remain preserved, that's it. The magnitude should
Can you just for just a foolish thing to ask, but can you please define norm for 1 second?
the magnitude of a vector is called the norm.
If the components are x1, x2, x3, root of x1 square plus x2 square plus x3 square.
I mean, I don't know the mathematical part of it, and I wouldn't explain it in mathematical way either.
When
So say that
what
the
do we
norm
call
of a
when,
vector is just the magnitude of that vector. That's it.
so what do we call a vector when okay, we call it unit vector, no? When the direction is preserved and the norm is 1. Unit vector is the one
Yeah,
vector
the
with
direction gets preserved and your norm is 1, yeah.
norm is 1. Fine. Okay.
this phenomena, this thing will also replicate when the vectors of this basis or this new I and j cap are equal, but they are still orthogonal. Then also this phenomena should replicate.
Sorry, I missed that. Can you repeat?
What I am saying is, for a matrix, if they are the column vectors are perpendicular to each another,
Hmm.
plus they are of the same magnitude, then also this phenomena should replicate.
Why is the only question?
No, it will
Yeah.
replicate that I'm able to see. Like consider that they are not affecting any. No.
Then,
And
like,
won't they scale?
won't the vector's norm get multiplied by the norm of the?
A scaling will happen, yeah. So
Yeah, I think
the
so.
magnitude has to be 1. That's why.
Yeah.
Scaling will happen.
For
If
Maria's question, she wanted to ask a very simple question. Right? She asked us, why should the vectors be norm? Why should the columns of the matrix be unit norm? Right? So, the matrix can be viewed as where I cap is going to and J cap is going to. Let me look at it in R2, right? So, if I cap is getting what is the norm of I cap?
1, yeah.
And we know that we want a matrix such that the norm is preserved, right?
Yeah.
So what does that mean? The output vector given the input vector as I cap, I want the output vector to have norm
1.
Yeah, 1.
So that's why the column, that's why I cap should be mapped to a norm 1 vector. Do you understand that now?
Okay, maybe we can elaborate on that.
Okay, we are now mapping it. Treat the matrix as a function. Fine. Treat matrix as a function.
Like,
we are giving an
why
input.
isn't that you can think of I cap and j cap as components of a vector, right? So why is it that when we try to generate a vector having unit norm, we need the components to have unit norm?
No, forget about unit norm. You know that the norm of I cap is 1. And you're saying you want a matrix such that the norm is preserved. You want that 1 to stay 1 even after the transformation. That means whatever I cap gets mapped to, the norm of that vector should also be 1.
Can we take an example? Can
No?
we take an
Okay.
example?
Yeah.
I think the example would be better. Maybe we can write that on.
And what Atharva is trying to explain is, now I get the question at least. So what Atharva is trying to explain in there, that we should take the two vectors of the matrix should be orthogonal.
But I think
We
first
don't
we
know
should
why.
understand, yeah, I think
Yeah.
we should understand why first they should be unit vectors, because that is more easier to see. After
Unit
that,
and
we can think,
orthogonal.
yeah,
Unit
they
and
should be
orthogonal.
unit and orthogonal, yes, but how?
Exactly.
Why?
Why?
We do not know why.
Yeah, maybe can I share my
So we
screen?
have we have seen this on GeoGebra that it requires to be orthogonal and unit vector. We have seen
We
this on
haven't
GeoGebra
seen anything on GeoGebra as of yet.
or anywhere.
So we
Okay,
haven't.
just beginning. Fine.
We are just beginning. We are just figuring out why for everything.
So
Why?
just a this is just a suggestion. We need to cross check it. Fine.
Yeah. So we need to figure out why norm equal to 1 and why orthogonal.
Correct.
So Maria has a doubt in that why norm equal to 1, and we are trying to take an example and to see that what happens when your columns have the norm 1.
Yeah, something that I think about is that yeah, when you're no, okay, no.
Yeah, go
Yeah,
ahead.
if you're like if the components of the vector no, okay. Sorry. I know. Yeah.
Just
My
gather
bad.
your thoughts and then maybe
Can you hear me?
No,
Yeah.
I was actually thinking on the go. Yeah.
Yeah, okay. So given this as a matrix, right? We know, what does V1 tell us? V1 is nothing but where I
where
cap
our
gets mapped,
I cap will go. Correct.
gets transformed, right?
Right. And same with the V2. So V2 actually carries the information. I like to think of a matrix as encoded information. So the
Yeah.
first column tells us where my unit vector in X direction goes, and the second column tells me where my unit vectors in the Y direction goes.
Yeah.
That's it.
Perfect. So now think about this. You want to find a matrix such that the norm is preserved, right?
Correct.
What is the norm of I?
1.
Is equal to norm of 1, 0, which is nothing but 1, right?
Right.
Agreed, Maria?
Yep.
Yeah. The same thing
Yeah,
for
yeah.
J, right?
Yeah.
Right. Norm for J is the same. Now, you know this V1 is where I cap gets mapped to. And you know
Yeah.
you want to preserve the norm. That means V1 should have the same norm as I. V2 should have the same norm as J. That's what you want, right? You want a matrix such that I want to preserve the norm. Well, first, let me preserve the norm for I cap and let me preserve the norm of J cap. That's what I'm telling you. Let V1 have the norm of 1. So V1 should have norm equal to norm of I cap. Why? Because this is what we want. We want a matrix that preserves the norm after the transformation, right? Do we agree on this?
So
I mean, we had two things, right? Rotation and scaling. We said no scaling, only rotation, right?
Exactly. Exactly.
So does this make sense, Maria? That V1 should have norm equal as the norm of I cap. That is 1.
I mean the only thing that I kind of think about is that like if you have a vector yeah, something that I'm not even sure it's right. Like the
Can we
yeah, so
example, Vinay, can we take an example where the V1 and V2 have norm equals to 1? Let's take, let me just do vectors where the norm is 1.
So 0.8 and 0.6. 0.8 and 0.6 would be 1, is it? 64, 36. So that will be. This is norm 1, right?
Yeah.
And as I think Davis Smith sir said, 1 by root 3, 1 by root 2 and 1 by root 2 would be 1 more.
Yeah, this is right.
0.707.
Right?
Yeah.
So this is a matrix which maps I cap to 0.8, 0.6 and J cap to 1 by root 2, 1 by root 2. Well, there's nothing else for me to say here, right? It's just visual. I mean, you just have to look at you just have to connect three things. I cap has norm 1 and you want it to transform such that it remains norm 1. So obviously, since the matrix is holding that information, the first vector that is in that location should hold norm 1, right? I don't think I can say anything else from now. Think about it. I mean, maybe it's not very clear right now, but I think it's quite clear, right? We want to preserve the norm, and the only way you can preserve the norm is make sure that the vector that is V1, which is 0.8, 0.6, should have norm 1, right? If I cap is norm 1, and you wanted to preserve the norm after the transformation, V1 should also have norm 1. If even V1 is not norm 1, think, okay, let's go the other way. Say the norm of V1 is not
Hello,
1. Yeah.
Hello, Sriman.
Yeah.
I have said something. It may help in this. Could you please look at?
Yeah, I'm seeing. I'm just loading. Are you ever able to see my screen?
Yep. Visible.
Like what he wrote is way more convincing. Like it's a mathematical proof that actually makes sense. Like there's no intuition, but yeah.
I think intuition after this we can't really push also. So
Let's say now find the norm.
Like the only thing that I thought of was that like if you like that's not correct. I guess like if you want to preserve the magnitude of something, you need the components also should to preserve
what does that mean?
the
What do you mean by that?
same magnitude. Yeah.
What do you mean by the components of a vector?
I mean, like when you decompose it into two directions, then there are two components.
I must say one thing, there is a mathematical aspect to it. Let us not try to make a geometrical meaning out of it. There is a reason why we are taking I cap and J cap and norm to be 1 in this case, so that the magnitude is equal.
Yeah, I think it's easier to see if they're not actually norm 1, right? What happens if V1 is not norm 1, right? Say this is 1 and 1, right? Then you wanted a matrix such that any vector I pass into it, it preserves a norm, but it is kind of defying in the first step itself. I cap is getting mapped to 1, 1. Norm of 1, 1 is root 2, right? Am I getting that wrong? Root 2, right? Yeah.
Correct.
So simple. I mean, it's just saying that even the first vector that I take as example, it's not having the same norm after the transformation. Does that make sense? Because you want any vector that you put into this, it should preserve the norm. But even I cap is not preserving its norm. So I can't expect any other vectors to also preserve the norm. Yeah. Okay, let's move forward then.
Yeah,
Think about
take
it.
over. Yeah, sure.
There's a simpler geometric proof we can use using trigonometry that we learned in high school, right? So maybe if Srivinay, let's draw a circle, right? Let's draw a circle and arbitrarily pick a point, any point, and of course there's an origin, and then pick a point and let's call it coordinate system XY, right? Anything on the circle, and let's give it a coordinate X and Y, right? So what will happen now if I connect the origin to that particular point? What will be that using Pythagoras theorem, right? So X
Square
coordinate
plus.
This is equal to cos theta, y equal to sin theta.
correct. So let's do that, right? So you can say X, then there's a vertical bar that is coming out, call it Y. Let's call this theta. The angle to the x-axis is theta, right? So the distance from the origin to that point on the circle is square root of x square plus y square. We all know Pythagoras theorem, right? And it's at a angle theta to x-axis, right? Okay. Now we have to come up with a matrix that is actually going to rotate this vector, which is located at xy. So if it rotates without changing the magnitude, what should happen? The resultant vector should lie somewhere on this circle. Otherwise, we are duality, right?
Correct.
You know, the circle, any point we choose in the circle, that we know that it is not changing the norm. If it is remaining
This is
under or
actually
going above,
pretty
right?
convincing, yeah.
Right. Okay.
Makes
Now
sense. Yeah.
let's rotate this. Let's pick another point above this xy and let's call it x dash y dash, something like that, right? So
Yeah,
let's
so if we take like our, yeah, so now it makes sense. Like if you want to shift it to, yeah, some other point, the components
let's
themselves
add an
should
angle.
have norm one, like, yeah,
Let's
okay,
not
yeah,
even talk about norm and all that. So this is theta, right? Theta could be
yeah.
anywhere between 0 to 2 pi, we don't know. Let's rotate it further by another angle called alpha, right? So Srivina, if we add another alpha on top of theta and then draw the line, and wherever it touches, we call that x dash y dash.
And the angle is alpha plus theta.
Yeah. So it will be alpha plus theta to the original kind of x-axis or our basis vector, whatever you want to call it, right? Okay. Maybe if you put like a acute angle, it will be slightly easier. You know, alpha plus theta, if you keep it less than 90, it will be slightly more intuitive. You can do that, but let's just, for ease of mind, then we can generalize it, right? Now there's an angle alpha between these two vectors, right? So that means what it means is we are rotating the original vector by angle alpha. Correct. Now
Yeah.
let's take the x coordinate and y coordinate. What is x dash?
X dash is cos of theta plus alpha.
Yeah, correct. Let's write the now. So cosine of alpha plus theta, right?
Mm.
What is my height?
Sine of
Sine of alpha plus theta. Okay. Now, what is the magnitude of this? We know if we take square of x, which is cos square
Yeah,
of
yeah.
L
Plus
plus
sine square
sine
is
square
1.
of something, sine square theta or sine square whatever plus cos square whatever is always 1. We know that from trigonometry high school knowledge, right? So now the question is the relationship between the original vector, what we can do to rotate vector xy by an angle alpha. So what was x originally?
It's
X was,
easy
see, x,
to think that when you preserve the norm, you should get the vector along the same circle. So the two components, when you split it up, like should have the same norm as that of the circle. I mean, that's what I understood when you drew the circle. So like I think my doubt kind of got cleared. Like, yeah.
Sir, what did you write? Just wrote Srivina x dash is equal to cos of alpha by theta.
It's alpha plus maybe. Yeah.
Alpha plus theta, I guess.
alpha plus theta, yes. Within bracket, yeah. Yeah. Then sine alpha plus theta. Yeah.
So yeah, you can think of when you're preserving the norm as moving the vector along the circle. and then the components themselves would be radiuses of the circle, and they should have them when you add them up will give you the same norm. Yeah,
Now
that means
what was the original xy? Original xy was sine of theta and cosine of theta. I mean, sorry, rather x coordinate was cosine of theta
cosine.
and sine of theta. Now observe these two, right? We had the coordinate cosine of theta and sine of theta. And after rotating by alpha, it becomes cosine of alpha by theta and sine of alpha by theta. Right?
Yes,
so,
sir.
right. So now we need to come up with a matrix that actually achieves this.
Davis, I had like a small doubt. When you, is it okay if we talk about it now or after?
Yeah. We can talk. Yeah.
So this part is clear, is it, Maria? Are you convinced about the norm part at least?
Yeah, I'm pretty convinced about the norm part when you
Yeah.
think about it as something that lies along the circle, and then
Yeah. So when you said scaling and rotation, right?
No, I understood the whole discussion, but not the last point that we got a matrix. What is that matrix?
Matrix is basically contains the information about the linear transformation. So basically what happens is when you multiply a matrix, let's call it a linear map, you're taking it from one vector space to another, right? So what happens to that vector when it goes through that linear transformation? Remember, matrix is a function.
Yes.
So linear transformation is a function, and we are defining that linear transformation in the matrix. So if you give me a vector u, multiply by matrix M, which is a linear transformation of the vector u, it is going to make that vector u to V after the linear transformation. So let's say my linear, if I give you an example, my linear transformation is 2 times x plus 3 and y is 3x plus 4, right? So I can always say I'm multiplying each vector by, let's say, each coordinate by 2, then adding something. Right? So that's what we typically keep in a kind of a linear transformation, isn't it? Like, so my ij after multiplying by matrix M is becoming, let's say, 2i plus 3j, and then whatever, 4i plus 5j.
Yeah.
Right? So
Yes.
that's linear transformation, right? So I can do whatever it is, a linear combination. It is linear. It is not changing. It is not making it non-linear.
Yeah.
So that means this matrix is basically a function which is kind of a linear transformation. Now, what we are saying is this matrix, when it is multiplying, it always is a function, can be simple function, can be composite functions.
Okay.
Right? The fundamental functions that happens to a vector is either a rotation or we are expanding or contracting. Basically this, and most of the time it will be combination of both. Most of the time. But there are two special cases where it only does one. Either it expands or contracts, which is the eigenvalue example. Ax equal to lambda x. So the direction is not changing. So there is no rotation whatsoever. Only it is changing scale. The other example is where direction is only changing, but the magnitude is not changing. So there is no scale, but only rotation. And most of the time, what we'll come across is it's doing both. So there is always some scale and then there is some rotation. So in fact, that is the 3 blue, 1 brown video actually talked about, right? We should see this matrix or linear transformation as what it does to the unit basis vector. So if you take a 1, 0 and you observe what happens to the 1, 0, how the, I guess that's what you're calling as ij, I cap, j cap. I was not part of that. But that is what is happening. Like, so if we take my unit basis vector, which is very simple x-axis, what it is happening. So what we'll see after you multiply in this example, it will increase the length of my x coordinate by 2 and y coordinate by 3, right? So, and then 2, 3 will form an angle which is tan inverse 3 by 2 because the height is 3 and right. So you'll see it rotated by an angle which is tan inverse 3 by 2. And it would have also resulted in a scaling. What is that scale? 2 square plus 3 square and the square root of that, which is 4 plus 9, square root of 13. So that means that's around 3 points up. So it will, if my original length was 1, it will end up being 3 point something. So that means it has achieved, it has rotated as well as it also. So it's almost like if you take that original dough and kind of somehow kind of rotated it and then also stretched it forward. So it has combining both the operations. So essentially, for me, when I understood, I thought matrix is a function, and there are two fundamental operation of function, basic unit functions, which is scaling and rotation, and it is doing both. But if there are some special cases, or rather simple cases, where it will only do rotation. Okay, so without even, if I create a matrix called
No, the thing was that I understood is that we only know a matrix as a function.
Yeah.
We do not know the entries of the matrix. I guess we were kind of trying to predict the entries of the matrix, given this condition that only rotation is happening.
Correct. So those contents of the matrix is basically nothing but an expression of that function, right? Because it is a function, what is content inside it is, what is a function? It is either multiplying something or you're rotating. That's what we're saying.
Okay, so the function is only the function. If we just look at the function, it will become pretty much clear to us. It is only rotating. It is only doing the rotation application. And can you explain this with the help of circle we drew? And we draw 2 points x dash and x dash, y and y dash.
So the best part is if we create a matrix called very generic matrix actually. The matrix contain cosine theta. So I think
minus sine theta, cos theta.
Yes. So how did you come to that?
I learned that that's I just knew it. That's it. I just knew that it's a rotational matrix. I think I learned that in maths too. I remember that. That's it. Nothing intuitive. Just some remembrance facts.
We should derive it fundamentally. Like if I take matrix and rotate it by theta, what is happening to the x coordinate and y coordinate? So it's pretty intuitive, right? So if we take this radius of the circle is x, then my projection of that x on the x-axis is x cosine theta.
Yeah.
And the projection on the y-axis is x sine theta, right?
Or cos theta or sine theta, yeah.
And the special case is when x is equal to 1, which is the unit circle. So if I take x equal to 1, then it becomes cosine theta and sine theta, right? That's again a special case of unit circle, right? So this is very natural. Now what happens is, what is its 90-degree angle? If I take a vector which has a projection of sine theta, if you do a 90-degree, intuitively, if it is in the first quadrant, 90-degree of that will remain in the second quadrant. And the angle, because they are orthogonal, if the angle with this is theta, this is 90 minus theta, then you can actually come up with geometry, right? So these are all axioms of geometry, right? So you can actually find that it is not difficult to find that the x projection of the other vector, which is orthogonal, is actually minus cosine theta and sine theta. Then what you're doing this
actually this idea can also be used to find we try to remember, right, what sine of 90 minus theta is. So if you actually do that in the coordinate system, you can actually figure that out. I just realized that when you explained, because when you draw a perpendicular, it will lie in the second quadrant. Then your components are cos theta, sine theta, then it becomes cos theta minus sine theta.
I think when I was in school, the teacher told us add sugar to tea cup, ASTC.
Yeah.
So that means in the first quadrant, all things are
all positive, sign negative,
then cosine, and then only tangent in the fourth quarter, right? So but actually you don't need to remember anything. That's what I always say. Look at it. X is positive, Y is positive.
First quadrant.
Right. And in the second quadrant,
X is negative, Y is positive.
So why we need to remember it? All we need to know is x axis is always the cosine projection, and the vertical is the
Y-axis is the,
You don't
that's
need to remember
actually
anything.
really nice. Like, yeah,
Yeah,
that's an
don't need
easier
to
way to
remember.
remember it.
Yeah, all we are saying is going left is negative, going right is positive, going up is
So in
positive.
the third quadrant, since both are negative, your tan will become positive. Yeah. Yeah.
Yeah.
Okay, that's quite cool
So
actually.
why you need to remember plus divided by plus is plus and plus divided
Yeah,
by minus is minus.
yeah,
You
yeah.
don't need to memorize anything. It's pretty trivial, right? So I think this is what I actually learned when I started to learn linear. I realized no need to mug up anything. It should be fundamentally derived from
Something
first.
you can think of. That's
So
actually,
actually, what basically we are doing that we first took the projection of a point xy on x-axis, and then we took the projection of the same xy on y-axis.
Yeah.
And
when-
representing in the terms of theta, of course.
Correct. And when the x is 1, that means my radius is 1, or rather my in Pythagoras theorem, that hypotenuse is 1, that's a special case, just to make it easy for the mind. Then the coordinate becomes cosine theta, x coordinate, and y coordinate becomes
Sine
sine
theta.
theta.
Sine
Right.
theta.
And let's assume for simplicity, theta is between 0 to pi by 2 because it is in the first quadrant.
Okay.
Just can
Okay,
we-
okay. Now
just-
I'm kind of getting the picture. The broad picture is that we have got an input vector. Fine. Let us keep it aside for a while. So what is going to happen with that input vector is kind of contained in the function itself.
Correct.
And that function is going to represent what it is going to do in the way that it is going to rotate our v1 vector to the position of v2 vector.
So very simple. So think of something, if I put cos theta sine theta, it's a vector, multiply with m, so that way it ends up being what? Any
Minus
angle, alpha. So it will be sine cosine theta plus alpha
Yep.
and sine theta. Assuming that alpha is small, so that way alpha plus theta is less than 90. Just keep it simple, so that way let's not complicate it, right? So then we know from the knowledge of trigonometry, we can actually, what do I do? What matrix I need to multiply to a vector? So that way, so it's almost like ax equal to b, right? I mean, x is a vector. Find the a, so that way when I multiply it, I get the vector that I want.
This is, actually magical. This appears magical. That is, things are so nicely, kind of arranged. We never could. Words would fall short to appreciate the beauty of linear algebra, the way they are arranged. We have got two vectors of a matrix. All the information is contained in there. What is going to happen with the vector v1 of the matrix? v1 is going to get rotated to v2, and that matrix as a function is going to rotate yet another input vector to an output vector, rotated in the same fashion to an output vector, isn't it?
Yeah. So here, is I guess apparently intuitively, if you think about it, you are taking, let's say, some kind of I always call this if you go to Domino's, get the dough, let's say somebody has like a unit length, right? Let's say you're making a bread or whatever, right? You go to Subway, you will see that they'll kind of lay them. So if you take that vector and you're trying to rotate, intuitively and it's in a 2 coordinate system. If you want to rotate and you have to lie, so you need to make sure you maintain balance, because if you don't maintain balance, then either it will stretch it or it will compress it. I mean, intuitively, right? I mean, if you really think of a physical object, that vector is a physical object. Like I always say, take a dough and it has some length, 1 meter or 1 centimeter, whatever it is. 1 meter is probably, you can hold it by hand. Now you have to rotate it by applying some kind of force, right? What is that transfer? It actually, think of physically what happens. If somebody tells you make it 2 meters, what do? You actually will apply a force,
linear force,
that direction, right? See why I'm saying think physically, so that we can relate to that concept. Otherwise, it just becomes some abstract, right? But if somebody says squish it, so you'll apply force, so that way it will get squeezed to half of its length, right? So similarly, if somebody says rotate, what will do? You will apply a force without expanding or contracting. So it looks like, you have to apply the force uniformly. If not,
It will not expand by its
it
own
will expand
multiplier.
or contract. Yes.
Okay. So what basically we are trying to do here is to kind of study the properties of such a matrix, which is just going to rotate the input vector and not, kind of make a
Change the magnitude
of it. We are trying to study the properties of such a matrix or to say function. Okay, nice. Up to this point, at least, I guess everybody would be agreeing.
Okay. Now you can put arbitrary elements A, B, C, D. It's like a high school, right? We now understand the problem. We understand how to solve it, and we have some unknowns, and we just apply whatever knowledge we already know, either through matrix algebra, or if it's hard to decipher, then we go back to our two equations, two unknowns, and find can we solve those. So that way, on the left hand, on the right hand side, m, let's say vector is sine theta cos theta, and apply the m, multiply the m, you'll get sine of theta plus alpha and cosine of theta plus alpha. Now, this is where the knowledge of trigonometry will be required. That when you expand a sine of theta plus alpha, how can I express that as sine theta and alpha theta? I think it's given, right? So that is where we can apply that algebraic knowledge and trigonometric knowledge to actually derive all the elements of matrix. And I don't know if again, what we are trying to do is fundamentally derive it. We are not trying to mug up anything. Just pure first principle understanding.
Yeah,
I guess Chetan is trying to say something. I guess.
Yeah, I was just saying that it could be very hard for people to follow in the even the chat. I'm getting some messages. Can we just write down everything that we have discussed? And I know it was kind of free flowing, and I understand that. But can we just summarize everything and write this down so that people can read it properly?
I mean.
Everything that we have discussed till this point, whatever Labor Smith sir talked about, everything. For people who are following it, it was easy, but for there were people. Yeah.
Okay. Let me summarize it. Okay, let us write the point 1. We have got an input vector. Any input vector. We have got a function, that is the matrix. And of course, we have got an output. Today we are discussing input and output to be of same magnitude. Norm of V2. Output V1 dash, okay. Anyways, so what we are discussing today is that the input and output are having same magnitude but different directions. So what basically is happening is that we have got a vector. It is aligned in some random direction. We apply a function to it. That is to say, we multiply it with a matrix, and that vector gets rotated by an alpha degree or theta degree, whatever we may call it. Fine. Do you need to write it?
Okay, you want me to write that also? Okay.
Sure.
The initial question that Sir posed was just that the norm gets preserved, right? I mean,
I'm coming to that. I'm coming to that point.
It's a rotation.
I think
it wasn't part of the question, right?
I'm coming to that point.
The question part is pretty clear to everyone. It's just the free flowing discussion we had was hard for some people to follow. That's it.
Mm-hmm.
Do you understand? It was like a half an hour free flowing discussion where people were just silent. Nobody was participating. That was the reason for that.
Mm-hmm. Sure, sure. So we have got an input vector and we have got an output vector. The input vector has rotated by some angle alpha.
Mhm.
Have you written this thing at least? Rotation by input and output has gotten an angle of alpha, and there is no change in its magnitude. What we are saying, what we are here to study, is that by how many angle, what is the amount of angle, and all and everything that we could say about the the relation between input and output vector is kind of encoded in the function itself, or to say is kind of encoded in the matrix with which we are multiplying the input vector to. For example, let us take an example. First of all, maybe write this, and then we will take a very ideal example that we were just discussing, past half an hour. We were discussing an example of this situation. And we are yet to kind of write down the final results, that what are the properties of those matrices. We have just discussed an example to represent this thing, which is representative of this statement.
This is the right statement. This rotation is encapsulated by the matrix M.
This rotation is kind of encapsulated by matrix. Fine, you can say this. All the things that is happening to matrix input vector is kind of encapsulated in matrix M. Fine. So how it is encapsulated? We have got a vector v1. It is going to get transformed into vector v2. Now we are taking an input matrix which has got a vectors v1 dash and v2. Not v1. Let us not make it kind of confusing. Let us take it to be n1 and n2. We have got elements, columns of the matrix to be n1 and n2. Column of the matrix are n1 and n2. Okay. So what we are saying, that we are for the sake of convenience and for the sake of understanding, we are rotating vector v. We are rotating the v1 vector by a 90 degree. Fine.
So
input.
So Nishant, so this is where we'll kind of prove it. Actually, we'll derive the formula. So if we go back to that original diagram that Sribin did, right? So original axis was x-axis. So our original vector, that xy, let's call that v1, right? So v1 vector had an angle theta to the x-axis, right? It's right. Now we rotated that vector by angle alpha. So that way basically the coordinate became cosine alpha plus theta and sine alpha plus theta, right? So in other words, my v1 vector, if we are assuming this x to be 1, so how do we take a vector which has x-axis, x coordinate cosine theta, sine theta, multiply by m, so that way I end up having cosine theta plus alpha and sine theta
plus alpha.
Let's express that equation. And my matrix M is, okay, so from a compatibility standpoint, matrix is going to be 2 by 2, rotation matrix. Vector has dimension 2 cross 1, and the resultant will be also 2 cross 1, right? So when I take a matrix 2 cross 1 multiplied by 2 cross 1, I'll get it. So we know that matrix has to be first M V1 equal to V2. That part is clear?
Yeah.
Right? Okay. Now we don't know the M. So it will be 4 elements. Let's call it ABC, D. And we will now use very simplistic approach to find what those values, magic values, ABCD should be. So that way it achieves only the rotation objective. Right?
Of course, there is something magical about that matrix. That's why we are so much
We'll find
interested.
out soon. Believe me, we'll only use high school knowledge. nothing else.
As was eigenvalues and eigenvectors magical, you know.
We didn't know about that in high school, right? So now let's take what is Srivinay, V1 is x-axis, x coordinate, y coordinate. Remember, x is 1. So projection on the x-axis was cosine theta and sine theta.
Cos theta, sin theta will give you cos
Yeah.
theta plus alpha,
Cos
sin
theta and then
theta.
a sine theta. That is right. So this is my vector V1 should be equal to
Cos theta plus
cos
alpha
theta within bracket theta plus alpha. Okay, theta plus alpha
within bracket
sine
and sine theta plus alpha.
Okay, now let's use trigonometry. If I remember correctly, sine A plus B, if you remember, cosine A plus B.
Sine A cos A plus cos A sin B.
Correct, exactly.
Wow,
So
okay.
let's actually expand it, right? On the right hand side, if we expand, this is equivalent to, now let's expand that cosine, theta plus alpha.
This is kind of proof of that.
Yeah, we see.
I didn't actually think it was this basic, like, yeah, but this is cool. Thank you.
We'll prove it actually. So
So
then,
intuitive, huh?
yeah, because
Now I kind of say,
you know,
I said out of memory, you know, sine A cos B plus cos A sin B, and I see that when
it will come out naturally. We don't need to memorize
when
it.
I started multiplying, I said, okay, both of them are same.
Okay, so cosine is actually, if you take cosine A plus B, you multiply cosine theta times cosine alpha minus sine alpha and sine theta. That's the expansion of the
Cos theta plus
Cos theta
alpha.
will play.
Okay, sine alpha into sine theta into sine alpha. Okay, and the sine is positive, so it will be sine of theta into cosine of alpha, right? The second term.
Second term.
Yeah.
Ah.
Cosine of alpha. Then cosine of theta plus cosine of
Sin A
theta
plus B.
and sine of
Cos
alpha.
A sin B.
Correct. Oh, very good. Now let's observe. This is the right hand side. Let's now actually do the row and column multiplication that we do. Now let's focus on the left hand side. So if I take matrix multiply with a 2 by 2 cross 2 cross 1, I'll take the first row multiply with the first column. Right.
Cos A.
Right. So what will I get? I'll get A cosine theta plus C sine theta. That's my first answer. The second answer will be B cos theta plus D sine theta. Okay. Now LHS equal to RHS. Now let's observe. Okay. So cos theta I see, right? Yeah, if you do it that, nice. So what's happening? I can clearly see cosine theta. So that means A must be cosine alpha. For this to be true, right?
C should minus cos minus sine of alpha.
So yeah, it'll magic will appear now. Okay. Then the bottom part.
Minus C is equal to minus sine of alpha.
Yeah, minus, yeah. Then B cos theta. So that means B should be cosine alpha. Right?
Sine alpha.
Cosine or
Sine theta, right? Sorry.
let me.
Okay. Here we have cos theta and we have cos alpha.
So it's we can theta plus alpha or theta alpha plus theta are same thing. We can
I
write
know cosine A plus B is cosine A into B minus sine into B.
E is sine alpha.
B sine alpha. Look the second term, na?
Yeah.
In the right hand side matrix, there is a term
Yeah,
cos
yeah,
sine alpha. That's
B is cos alpha.
Let's put them
This
into.
is nice, yeah.
this matrix is a metric matrix, at least for this 2D.
Okay, one observation we have.
But it's minus, not exactly symmetric. It's minus with a minus sign.
Okay, okay.
What's the determinant of this metric?
Okay,
One.
it is 1.
The minus plus, yeah.
So if a determinant of a matrix is 1, it is not going to do any.
Mm.
You know that scale is not going to change.
Correct.
And then these two vectors, you plot them. What will be the angle between these two vectors? So imagine you have a cosine alpha, sine alpha, right? And then you take a mirror image of that sine alpha. Let's say you take 1 and 1, very easy, right? I mean, let's take alpha equal to 45 degree. So cosine alpha is 1 by root 2, sine alpha is 1 by root 2. Then what is negative of 1 by root 2? If you look at the cosine table, it will be at 100 degree. If you actually plot it, you will see that they are 90 degree. If not, take the dot product.
Yeah, that's what I thought. Yeah.
So what do you expect the dot product to be?
So
0,
this
right?
is also quite interesting to note. Means earlier I was not able to see that determinant of this metric has to be 1. Intuitively, we linked it somewhere before, like determinant is like scaling of the areas between two vectors. But here this thing also, like we are saying the magnitude should be same. So determine the space, because determinant is linked with the space that is scaled up or scaled down. So it should also remain constant.
Yeah.
So that's why it has to be 1.
You see, we didn't have to mug up anything. Everything was derived. And the solution had nothing to do with theta. So that means it is generic. Theta could be anything. The solution remains with what is the rotation. So now we're using this. Now imagine in a phone, you want to rotate an image. What should be this content? You know, sine of 90, you plug in the angle that you want to rotate is 90 degree, right? 1. So if you put alpha equal to 90, you want to rotate an image by 90 degree, you know the answer, what matrix you should multiply. Right? Cosine 90 is what? Sine 90 is 1, cosine 90 is 0. So 0, 1, minus 1, 0. That is what our phone is doing behind the scene to all the pixels. When we, do this.
Rotate the image.
Now, here is a trick. There, if your phone has typically 16 is to 9, because 4 square, 3 square ratio, right? So in movies also you would have noticed they are always in 16 is to 9 ratio. If you remember, like somebody from if you've done video editing and all that, there's this 4 is to 3 or 16 is to 9. You say why, right? 3 square, 4 square, Pythagoras theorem, 5, 3 square plus 4 square. So anyway, so all, if your phone has, let's say, certain, usually the width is less and length is more, right? So when the picture is rotating, so of course it's not, it's a rectangular thing. When you rotate, so of course it will kind of adjust that ratio, But if it is, you're not changing the magnitude, so you can just pre-multiply, because scale is just, you have to apply that scale, that's all. So the ratio between 16 by 9, you need to keep it. So what you need to do here to increase scale by 16 by 9, you'll notice that it is 4 by 3, 4 by 3. So on both directions, and that's it. You just need to apply that. And in fact, ultimately, that is what the phones are doing behind the scene. So I always say that, the best way to learn is, we use it every day. We just don't know it's happening. Right under our nose and eyes. Seeing Illinois every day.
Now I'm considering one point. I'm not able to see in my mind that for all matrices whose determinant is 1, will they only like rotate? Just means keep the magnitude of input matrix vector same. Under what circumstances yes and under what not?
Okay. So what we said is, if it is a rotation matrix, then the determinant must and have no impact on the scale, then the determinant must be 1. Now you are doing the converse.
Yeah.
If I find a random matrix,
Yeah. Whose determinant
determinant
is 1.
is 1,
Yeah.
but the vectors are not orthogonal. See,
Hmm.
remember, there's a special property of what we found. We
Yeah.
found a special matrix where the transformation, basically the functions, it's a composite, right? So
Yeah.
they were two orthogonal, and actually, to be precise, they were orthonormal also. If you notice,
Yeah.
the magnitude of each of this column is actually also 1.
Yeah.
They are orthonormal. They are not only orthogonal, they are also of unit dimension. So then they are also special case of orthogonal vector. They are actually orthonormal. By the way, I was not in the class. I'm sure when the matrix was decomposed, Q lambda, Q transpose, I think it was discussed. So the matrix Q is of this type. It only contains orthonormal basis vectors.
Yeah.
I'm trying to link the dot to the previous session. Unfortunately, I was not there, but just by sheer memory from 2 years back.
But can we say like for this thing, determinant thing, if we see from the another end?
See if they are basis vectors or not. Na? Check it out.
Let's take an example in this also regard.
So take random, okay, give example, right? So what can be, okay, 1, 1, 0, 0, right? So how many, so come up with some random examples, you can take anything, just ABCD where AD minus BC equal to 1.
It's
How many?
zero,
Yeah.
determinant 1.
So let's do, try to break the system, right? And then observe what is happening there.
Identity clearly have that. Yeah, yeah, 1, 1. Okay.
So clearly you see it's 1 minus 4, determinant is minus 3. The other one has to be, yeah,
1, 3.
2 by 3 minus, so
3 by 2. Okay, fine.
yeah, so it will be 0 actually, right?
0 हो गया ना ये
4 by 3. Yeah.
1 होना चाहिए.
1, 3 in column. That would work, I guess.
Yeah, 1, 3, correct. 1, 2, 1, 3. Yeah, 1, 2, 1, 3. Okay. Okay, this also.
1, 3 is the second column. Yeah, 2 by 3 minus.
So it is minus 1 by 3 now.
Do it minus
1, 2 in the first column, 1, 3 in the second column.
Correct.
Make it
No,
a
no.
minus.
Yeah, that's a, yeah,
just
that's a
make
good
it
one.
a minus.
1, 2, and 1, 3. You will make it good example actually. Easy to visualize also. So clearly the determinant of this matrix is 1. And if you look at the vector 1, 2, and 1, 3, 1, 2, so, and then 1, 3, 1 is tip, right? So clearly there is an angle and they are not orthogonal. It's very easy to, the dot product is clearly not 0. Now take a vector, multiply, what will you do? But take a any vector, basis vector, let's take 1, 0, a vector lying on the x-axis, right? This is our I cap, I guess, right? That's what you guys call.
Yeah, 1, 0 goes to 1.
1, 2. So 1, 0 is going to 1, 2. That means it's almost rotating, but the magnitude is changing or not? What is the norm of the previous vector? 1. The norm of this vector is actually square root of 3. Square root of 5.
5.
So that means the magnitude is changing.
Yeah.
It's actually doing rotation plus scaling, both. Agree?
Yeah.
This is actually the heuristic, not the proof. So you'll find out that you can find like a matrix or a linear transformation whose determinant is 1, but if the eigenvalues and when the eigenvectors are orthogonal, then they display that property.
With determinant 1.
Yeah, because you will see the, what do you call it? The eigenvalues are like symmetric, in a sense, equal value, conjugate pairs, right? Otherwise, it will not maintain harmony in both the dimension X and Y. That's intuitive. You have to think like the force that I'm talking about, right? So if you want to, let's say, take a circular dough in dominoes, and you want to increase. So what you have to do, you want to maintain a circle. So you have to apply the force equally on both X and Y axis. So that way that dough, which was like small one, will become big. It's intuitive, right? And you have to apply equal force on both dimensions, which are orthogonal to each other, and should be equal. If it is slightly unequal, then you will get an ellipsoid. You will not get a circular pizza. It's pretty intuitive. You can, or you do roti or chapati, whatever you can think of. You will not get a circle, you will get an ellipse. So basically the force where you are going to stretch more will be your major axis, where it is less will become minor axis. So basically it will become an ellipse. So that means to maintain harmony, there has to be both, the direction has to be in sync, equal. Right. So similarly, same concept. Again, I'm trying to draw parallel, right? So that we kind of try to develop the intuition, right? I think sir always says, first do the intuition, then the math, not the other way around. I guess what was discussed, I don't know. We proved it though, right? Or is it still?
No, I think proof-wise it's okay. I feel equal stretching in our sense has to be, okay, take a matrix. I know that this is where I had maps and this is where they had. So obviously these two have to be unit vectors.
Correct.
Right?
So remember, and plus the stretching has to be you're applying force in two direction and they have to be 90-degree angle. If you do these two force at some angle other than 90 degree, then you will not get the circle, is the concept.
Yeah.
The reason is when you are applying the force, when they're orthogonal, the dot product of one and the other is actually 0. So you are not really, kind of, this force is not impacting this one and this force is not impacting the other one. I think we talked about people from mechanical or whatever, like if you applied force to a metal object and you're trying to do that, I think somebody was there, stress, strain, discuss.
Yeah.
Shear, if you've done mechanics, some of you may be from engineering background in semester 1, Timosika, right?
There's a mechanics course.
Yeah.
Which I don't know.
Yeah. And by the way, you would have noticed there is something called a principal stress and principal strain diagram. That word principal has everything to do with our PCA. If it is not discussed, it will be discussed later.
Now I get the point why there is no structure.
Nishan, your
Vectors,
voice
Vishal,
isn't
vectors.
clear. Yeah.
So now I understand why there is a circle in Mohr's circle. I wonder why he has to take circle, you know.
Life is a circle, right? To understand life, you have to remain in the circle. If life is balanced, then you will be on the circle. If your life is unbalanced, you'll
Yes,
go
it's
off
an
the-
ellipse, yeah.
This is the philosophy of life, and it's also a matrix, right?
Correct, correct.
You scale too much and rotate too much, then too bad. Sorry, too much about philosophy. Let's go back to matrix. Remember, we say we all live in a matrix, right? So,
Correct. This transformation thing, you know, especially this rotation, rotatory transformation, I guess this has to do with the motion of robots' arms and different parts of the robotics.
yeah. And if you notice, most of these rotations, they're kind of, because they don't want to, for every motion, they have to create mechanical rotors, right? There's a discipline called mechatronics now, like mechanical
Mechatronic.
plugs,
Electronics.
If you notice, they have to define rotors, they're expensive and it's right. So you'll notice that they are orthogonal to each other, right? So either I can move my robot arm in this direction or that direction, because by creating only two rotary motors, I can span the entire space.
Correct. At that point of time, we were taught this, we didn't get this. You know, why we are kind of applying servo motor only for two directions. Because
anything more than two means you'll get the other vector as dependent. No need. Why will you waste third rotor? Now you know in some way, right?
and
Why
those two rotors, one
you
here
can
and one
reach an
here.
object by manipulating two rotors. You don't need a third rotor.
Correct.
You can take a alpha of rotor 1 plus beta of rotor 2 to reach an object, because you want to robot needs to grab an object, cup of tea. So the cup of tea is at a particular coordinate. So you need the alpha steps in here and beta steps on the other direction. So that way you can pick up the object, right? So same concept.
Mechanical engineering students never get this. Why a matrix is being used here, you know, and matrix multiplication to represent the.
In EM, engineering mechanics, when we saw tensor, a 3x3 matrix, it was hard to us to remember even
The
that.
strength of materials, correct.
Yeah.
Yeah, but think about it. So robot, I mean, just to stay on the topic, robot would have a sensor camera. It measures the distance between the object you want to pick up. That distance has to be translated. Okay, in order to reach from XY to some other place,
X dash Y dash.
distance, how much I have to travel. So it's kind of, I know my current location. To go there, what I have to take a path, right? You to go that path and make that transition, what multiplication needs to happen along each rotary. So you're kind of going that angle, but then how much on this rotary dimension or how much is the other rotary dimension? That's it. I need my X move and I need my Y move. Essentially, that's what it's doing. It's solving an equation to go from a space X
to a particular another space.
What should be the transition? The transition is basically nothing but a matrix, which is essentially a function or a composite function. I guess we learn that in reinforcement learning at a degree level. I have not gone to degree level yet. I have to wait for 4 months, but
yeah, I completed it. It's used, yeah. Okay, so we know that when the matrix has unit vectors and each vector is orthogonal to the other, right? That's what we want. So in a 2x2 case, it would just be so this is V1 and V2. We want norm of V1 and norm of V2 to be equal to 1, right? This is what we saw. And we saw that
the sine alpha, cos alpha, like, minus sine minus cos, right? That's what we saw.
And the dot product is always 0.
Yeah.
So
So the
yes,
general
we
form,
decoded that. Yeah.
yeah, general form, yeah, I think it's here, right?
In the general form, yeah.
Awesome. So for what happens for a 3x3 matrix? Can we get the same kind of form?
Yes, actually, that is correct. So, intuitively, you can actually take that answer, do it to a 3x3.
It seems scary for me, especially since I'm not very comfortable with trigonometry.
See,
Commerce.
Sir,
Dark
it would be
again,
really nice if you can give us a trigonometric class.
you remember the thumbs up ad, right? Older ad where Salman Khan used to jump from a cliff and all that, right? So Dark aage jeete, right? So you have to confront your fear, go through that, and after that you will see the high, right? Once you confront your fear, embrace it, and confront it many times, then it's no longer a fear. It's a come on, bring it on, right? And then after that, it becomes part of you. Then that becomes your strength. Then something else becomes the fear.
We did discuss quite a lot of trigonometry today, right? It was really nice. I mean, I just wish that we had written all of that down. The free flowing discussion on trigonometry that we had today.
See, the thing,
It was only high school, right?
Isn't it?
Standard 8 stuff.
Yeah.
Standard 8 stuff. Nothing more than that.
in
We
plus,
People don't learn it the way you were explaining that. That's the thing. So these notes will be really useful for people who might want to understand that. That's why I wanted everything to be there in the notes.
Actually, we use trigonometry because we wanted to prove geometrically,
Right.
and geometrically because we can visualize it, right? Instead of making it abstract, we can see clearly a vector is getting rotated, and when you rotate an arrow, it will remain in a
Correct.
circle. It's very obvious. You don't need a proof. It's obvious, intuitive. You can get it, right? And then we are taking x coordinate, y coordinate. That happens to be angle. So we
Right.
are essentially.
Actually, our question itself gets reduced to generating all vectors around the circle, right? Because we need to preserve the unit one off. Like when you introduce a circle, it becomes way more easier.
So I'll tell you what, there are two kind of measurement systems. So when you plot a dot on a graph, you can call it two ways. One is XY, it's a coordinate system. You can also express it as a polar coordinate. You can define
Yeah, R theta.
R and
Yeah.
theta. By the way, in Python, you must have learned, in order to represent an object on a space, either you can represent that as a coordinate system, which is basically x coordinate, y coordinate, and which are orthogonal to each other. Or I can express it as a radius, distance from the origin, and the angle it has with respect to the reference x-axis. I don't need a y-axis if I'm going to polar coordinates. So these, they're equivalent. Now what will happen is if I'm trying to find distance between two vectors, in the Cartesian system, it's easy. Why? Because I'll take, x1, y1, x2 minus x1 square plus y2 minus 1, y square and square root. So finding distance between 2 points is easy if you're representing those 2 points in a coordinate system. Because if it is polar, then you have to do r sine, then you have to do that, right? But I want to find angle between two vectors. It's tough in coordinate system. But in polar, it is theta 2, boom.
Yeah.
So in a given problem, if you're finding a lot of angle between vectors, code your points in a polar coordinates, you'll get computation faster. But if you're trying to find distance between 2 points, like you're doing clustering, you're finding Euclidean distance, then present them in a coordinate system. So this is why there is choosing how you represent that dot in your system, or a measurement system, totally dependent on the kind of problem you're trying to solve.
When I encountered, when I got to know that, okay, we are going to get to do integration and all in our maths 1, I guess, or maths 2, I don't remember. So I was expecting a lot of, trigonometric formulas there. But I wondered why are not why, I never encountered a question where used trigonometric functions. Fine. Now I realize that because this program is, this program constitutes of many non-mathematical background students as well. That's why they skipped trigonometry, because they would have to take a complete course on trigonometry as well. If they were to kind of put forward the questions related that we usually see in +2 level of integration. And almost all of the questions in there are kind of related to trigonometry only.
I mean, two such students are sitting right here, right?
Not really, I think.
So it's a nightmare for the PCM students, who kinds of somehow misses out or skips trigonometry. It becomes nightmare for them.
See,
Because
we never teach students why they need to learn, how it is going to help, right? Why we should learn polar coordinates versus Cartesian coordinates, right? So it starts with Euclidean geometry, right? So when we are taught in a school, it should be taught how we are going to, use them in real life. If not, students will lose motivation. You should teach first why they should learn before you're teaching them. Unless there is a motivation, like here, why you are learning linear algebra, because the fundamental building block of linear algebra is basically the entire machine learning. Everything is matrix and function, nothing else, right? So if you don't know this, you cannot call yourself a machine learning guy or a data science guy. I think you talk to 100 people from the industry, 90 people don't know what is a matrix. So then they're not data scientists, right? Then after you do linear algebra, then you have to understand probability and statistics. Only after that you can be like, your fundamentals are sound. Otherwise, you'll still go to stats model, sklearn, you do some package. That doesn't require a lot of expertise. You can go to Stack Exchange, copy a bunch of code. That doesn't make you understand. I mean, it's like driving a car and knowing how to build the engine from ground up, right? There are two different skills. So if you want to do an MBA and be a manager, just know enough to be dangerous, that's okay. But you're not a data scientist, you're just an analytics guy. So that is the difference between analytics and data science. People use these terms interchangeably, but they're not, right? Similarly, students who know what is the motivation, why they should learn, then they will have excitement. Otherwise, it's abstract, it's boring. So you have to relate it to everyday objects. How it is going to help them solve. Only then people will learn, otherwise not. Even in IIT Madras, I'll be honest with you, I've interacted with some of the instructors in math too and all that. Affine space, subspace, I asked, tell me in machine learning where it is used. No. But if you go to MLT, W transpose X plus B bias, what is that bias? W transpose X equal to is a plane, hyperplane going to the origin. If you shift it by B, that's your affine. And
okay, so we were discussing affine and we never used the word affine.
Yeah, I asked the question when I was in math too. The guy doesn't know, so don't want to blame them.
No,
So
Srivinay taught us that,
Yeah.
And Ankit kind of briefed us how,
Yeah, why should you learn affine subspace? Where it is used?
I had no idea, but they taught us.
So
I never took the name affine subspace.
Correct. When you learn a perceptron, right? So you realize that simple learner, right? So I think most of the people would have done machine learning theory or foundation, maybe. That is very
doing it now. I'm doing those courses now.
Yeah. So why that W transpose X plus B, right? So this is where, anyway, so most of the time we learn all these things. They're not told to us why they're useful and how they're going to help us in future. Otherwise, you'll then you're only studying to score marks. Then after 3 months, you encounter that topic, you don't relate. And that's where all the translation get lost.
I guess Atharva, yes, because it is also, we are also kind of translating it parallelly, and in Conics also, I guess you would have kind of read the same thing, that you're kind of parallelly translate some geometrical figure. Isn't it, Atharva?
Okay. Is today's session going to close now? Or?
Ketan?
I might have to leave.
Isn't
I
that so? Oh yeah.
So you are going to get calls from cosines, right?
Cosine.
I can't think of it. I was supposed to send that message to Chetan. I sent it on everyone. My bad.
There are signs from cosines. I had no idea.
That was nice one.
We were building on a Dimitri joke.
That was nice one.
Oh my god.
I like puns.
For the first time,
I love puns.
Devasmith is
Even
the best.
I like
He makes the best puns. Yeah.
He also gives really good examples as well. I mean, look at the pizza example.
Yeah, like you are actually really valuable. Like your process is pretty
Yeah.
cool. Like you have
Right.
like I learn new things from few people and it's nice having.
Yeah,
That's
I'm not able to join every day, but I want to. It's just work and other things keeps me busy. But yeah, at least I'll try to join as much as possible because I also learn, right? Because once you work and get older, I think you would realize very, very hard to learn. Second is very hard to retain what you have learned. Both. So life is a decay function, right? So every 2 years you'll forget half of the things you learned. So a half-life period in corporate life is actually 2 years or even 1 year. So if you learned in school, you're supposed to learn 100, you learned 80. By the time you graduate 1 year old, you learn 40. Then after that, 20, then 10. Then after that, you're basically worse than a fresher after 4 years.
It doesn't seem so, sir. When we look at you, it doesn't seem so. It doesn't seem
Continued learning is very important.
Yeah, that is why I'm in the program, right? I'm not here for degree. I think people who know in Coder, right? I joined the program to relearn, right? Not to get a job or whatever, right? So we are working professionals, but yeah, I mean, just to fill in the holes and gaps. And the Coder side was very useful. I think all the things and ideas and everything, all the dots were discussed, and I think slowly it starts forming. So the more and more you participate and start thinking, I think all these things will kind of, then you take the courses and, it's like you span the column space of machine learning and somehow the basis vectors will appear. That's what happens, right? So I think no need to question, just accept everything and then start thinking and try to relate. Most importantly, relate the points from different courses, right? Then it will be fun. Otherwise, we are taking it as but what sir would do is after this, he'll mix probability statistics with Python with linear algebra. That MCMC that he talked about is actually that Monte Carlo markup chain is actually statistics plus Python plus linear algebra all combined. So yeah, so then it will be fun.
I guess we encounter the question of that, okay, we are given a probability, in a probability space. Now I get what is the meaning of probability space. And I always used to wonder, why it is always getting added up to 1 only. Now, because it is in a space, it's getting added up to 1.
Yeah, another thing to think about is when I learn probability, it is saying what are the total possibilities, and then whatever I'm thinking of event of interest has some kind of constraint. It's not everything, right? If it is all possibilities, then it is okay. There is a chance that I will be successful 2 times, but total possibilities are 3. So then the probability of success is 2 by 3 because 3 are the total choices, and it's like MSQ problem, right? There are 4 options and 2 are correct, right? So same way. So number of events of interest divided by total number of possible events. So that's how we learn. Because it's a ratio, your total number of successes cannot exceed the total number of events. So that is why it is 1. Now, when you are studying different independent events, you are partitioning the space into disjoint, and they are mutually exclusive but collectively exhaustive. So everything has to add up to 1. That's the total loss of probability. But within that, you are kind of computing probability of event A, event B. Essentially, it's a set theory, right? And you are looking at the number of elements or possibilities within each set, right? So
So the crux of it is that we are able to do whatever operation we do because it lies on a space.
Yes. Yeah.
Nishan, what was your statement of unit space?
No, not unit space.
You said something now.
Probabilistic space. Probabilistic space. Questions often mention that okay, this data is in a particular probabilistic space.
Yeah, let's not get into this. Actually, it's called a concept of triplets. It actually combines major theory. There's something called a metric space. You may have heard about it. So it's called triplet. And there is something called a sigma algebra. If you want to get into deep math, sigma algebra, you'll probably come across in DBMS if you have taken DBMS. So all the SQL queries you write gets into relational algebra, and there is a sigma algebra. So there is a, but let's not discourage people. We should keep it simple, not get, things should be learned intuitively, then the math will follow. But if we get into math, then we get scared, then lose interest.
It was just an observation. Everywhere there is a mention of a space and there is a probability. My mind kind of connected that it is related to vector.
Just like vector as vector space.
Similarly, yeah.
Use the vector to span the space.
Yes, similarly.
Right? So let's, but if you're interested, I'll send you some information privately. That's really, advanced. I don't think in IIT Madras, maybe at a degree level, I don't think they'll go to that level. Even at a degree level, that's usually taught in master's or PhD level, basically. Or if you go to ISIE or some kind of a master's in statistics, then maybe they'll cover all those concepts. Or maybe MSc Math, they'll be covering it. Like topological space, you may have heard about in math, ring theory, those kind of things, right? So, but it's very abstract. So what happens is a lot of people get bored because it's so abstract. I mean, it's abstraction of abstraction. So it's like, then you're like totally lost. You're only writing equations. People think you're crazy. So it's better that in data science, we are always staying closer to real life data, which is represented by some phenomenon that you have observed and you have quantified and recorded it. And you're trying to understand the underlying process that is generating the data. You're trying to model the underlying process so that way you can, let's say sales is a process. It is giving you some number. Now you're trying to forecast. So you try to understand what is the sales process. So the sample that we have got, and then I want to understand that, then use that for my sales forecasting. And that will be useful for planning. And business leaders will love to get a solution that you as a data scientist are able to help them to make a business decision, right? And this is why it is fun. So it is helping businesses to navigate the world of uncertainty. We're trying to create, okay, my sales is a function of what my competitors do, what I do, what my products, right? So you're actually creating equation. What is my market share? So these X1, X2, X3 vectors are essentially these features. Now you're trying to express sales Y as a function of these vectors. Again, matrix comes to the picture. Whatever you do, all end of the day, it will be some multiplication, it will be matrix. Most of the problems. So this is why, what you're learning here is probably, fundamental to anything we do in life. If you want to stay in the field of data science or even business analytics, I would say. Business analytics, maybe you can get away, but data science, definitely.
I think I understand the foundations well, but I've not seen much application. So maybe it's time for me to start putting it into action. Yeah, you do. I think internship, the way the program is designed, I think I'm assuming most of you are in the DS program. I think Atharva is from IIT Ropar, right? I think in the degree level, there are internships. So great way to learn application is go to a company and do internship. That is where you'll see the real life problems being thrown at you. Then I think it will all kind of make sense. Then you would say, oh, I wish I had some work experience before I did the degree.
I mean, Tharva and the gang, they're getting an opportunity this December, right, Tharva?
Atharva is not.
We're not sure yet. Yeah.
Atharva, you are in second year or third year?
First year.
Oh,
Yeah.
long way to go. Yeah. So
Okay, I guess since we're not discussing anything important now, I think I can stop the recording. Else it will all be there on YouTube for everyone to hear.